Kids. All right, one more circular motion problem. We're spinning a bucket of water in a vertical circle. 0.3 kilogram bucket of water. We'll say that's the amount of the mass of the water. Radius 1.2 meters. What's the minimum speed to make it through the circle? And then if it keeps going at that minimum speed, what is the force that the bucket exerts at the bottom? Okay. So as always in this unit, our number one step is to draw a free body diagram. So we're going to have to draw it at two different spots, at the top and also at the bottom. So if I draw my free body diagram at the top, okay, there is the water. So this is where you guys got to be careful because, again, my free body diagram is always what is the thing that has the forces acting on it. In this case, it's the water. So this is the water. At the top, I would have the force of gravity going down. And then if it just barely makes it through the circle, that would be it. You know, the bucket isn't actually pushing down on it. If it was going faster, then the bucket would be pushing down on it. But if it just barely makes it through the circle, that's the only force acting. At the bottom, I am going to have force of gravity still going down, okay? And then my normal force from the bucket going up. Now, the reason I drew the normal force bigger, as you notice I did, remember, this is supposed to be going in a circle, okay? If it's moving in a circle, that means it has to be accelerating towards the center, hence centripetal. Centripetal acceleration means toward the center. So that means if it is accelerating towards the center, my Fn has to be bigger than Fg. If it wasn't, then it would snap at the bottom of the circle. And yeah, bad news, okay? But that is what's going on, okay? So first step, always this. Second step is to write my equation from my free body diagram. So at the top, I have the sum of my forces is just Fg, which equals MAC. Okay. Now I realize I give you a mass here, but I want to show you something. If I plug this in, okay, my m's go away. Okay, why is that significant? Well, let's say instead of this problem, I'm designing a roller coaster. Well, if I design a roller coaster, I don't want the minimum speed that it's going to take for my roller coaster to make it through the loop-to-loop to depend on the mass of the people. You know, because otherwise I would have to be like, well, sorry, you're too massive, you can't get on. Okay? But as you can see, it doesn't depend on that. If I do a little bit of math, remember this is v squared over r. So I get v equals the square root of r times g. So v equals the square root of 1.2 times 9.8. So v equals, let's do the math. About 3.4 meters per second. So the bucket, the water have to be spinning roughly about 7 miles an hour. It's 3.4 meters per second. Okay, that is a decimal. All right. Now let's do the bottom. So this was the top. Okay, so now this will be the bottom. Okay, so if we do this, I'm going to get, remember, bigger minus smaller. Fn has to be bigger because it's accelerating towards the center. Minus Fg equals mv squared over r. So if I plug my stuff in, I'm going to get, I'm looking for Fn minus 0.3 times 9.8, because that's my Fg, equals 0.3. V, I got to be 3.4 squared, and then my radius is 1.2. So let's do a little bit of math. 1.2 times 0.3. And then you have to add 0.3 times 9.8. And you get 5.88 newtons. So at the bottom, the bucket would be exerting this much force to keep that water moving in a circle. Buckets!